So one of the biggest, if not the biggest result in statistics is the central limit theorem. And it's going to basically state that a sample distribution, or picture 2, is a skinny normal curve if the sample size is large enough, being larger than 30. And, if this is the case, it's not going to matter what the shape of the original population is. So when you take a random sample from a population that does not have a normal distribution, the central limit there can be helpful in identifying the shape of the sampling distribution of the sample mean. Formally stated, the central limit theorem states, in selecting random samples of size n from a population, the sampling distribution of the sample mean, x bar, can be approximated by a normal distribution as the sample size becomes large. Here are a few illustrations from the central limit theorem. At the top of the chart, there are 4 different population distributions. Following each of these downward, we observe that the sample distributions appear more normal as the sample size increases. In other words, we observe the convergence to a normal distribution regardless of the shape of the population distribution. Once we get down to a sample size of 30, we see a tall, skinny curve, which looks very similar to picture number 2 from our sampling distributions discussion. For this particular picture, we don't actually need the central limit here because the shape of the population in picture 1 is believed to be normal. But what you see is that at each picture number 2, the normal curve will get skinnier as the sample size increases. So we don't need a large sample size for this situation because our population is already normally distributed. In a uniform distribution, we see that this population shape is flat. It would not describe heights, but maybe it describes other populations. But once again, as my sample size gets larger, it begins to approximate the tall, skinny curve of picture number 2. I don't really know of any populations with the shape of a U where we have for this picture number 1, but this is about as far from normal as you can get. So for sample sizes of 5, the shape of the sample mean looks like, a little kid wearing a bed sheet for Halloween. By the time the sample size reaches 30, once again, the sample means follow a normal curve. So as a recap of the central limit theorem, picture 1 will describe the shape of the population of the individual measurements. So maybe the population's normally distributed, maybe it's not. But the central limit theorem will describe the shape of the sample mean, which is our picture 2. And so this picture will be considered normally distributed if n is larger or if you have reason to believe that the original population was normally distributed. Remember, when you're looking at the distribution of a sample, the standard deviation will be the standard deviation of the population from which you're sampling divided by the square root of the sample size, and it's also called the standard error of the mean. So even if we don't select all samples, we can expect the mean of the distribution of the samples means to be close to our population mean. If the population standard deviation is sigma, the standard deviation of the distribution of sample means is sigma divided by the square root of n. So note that when the sample size increases, the standard error of the mean will decrease. So we'll use the Z formula when the population standard deviation is known or assumed to be known. So looking at this example, we have a quality assurance department for Cola Incorporated maintains records regarding the amount of cola in its jumbo bottle. The actual amount of the cola in the bottle varies a small amount from one to the next, and looking at records, we see that it follows a normal distribution with a mean of 31.2 ounces and a standard deviation of zero point 0.4 ounces. So we have a quality technician randomly selecting 16 bottles from the filling line, and the mean was 31.38 ounces. Is this a likely result? Is it likely that the process is putting too much soda in the bottle? Is the sampling error of 0.18 ounces unusual? So the first thing we're going to do is we're going to use the Z table to determine the probability. So in this example, we calculate Z with our observed value, our observed mean of 31.38 ounces minus my population mean of 31.2 ounces divided by the standard error of the mean. So that's going to be using this the population sigma, which is going to be the zero point 0.4 divided by the square root of my sample size, which is 16, and we find a z-value of 1.8. And so when we use that z-value, we can then find that about 4% is in that upper tail. So since that's about 4%, that means that we have less than a 4% chance that we could select a sample of 16 observations from a normal population with a mean of 31.2 ounces and a population standard deviation of zero point 0.4 ounces and find the sample mean to be equal or greater to the value of 31.38 ounces. So this means that we can conclude the process is putting too much cola into our bottles, and the quality technician should see the production supervisor about reducing the amount of soda in each bottle.